So continuing on in Chapter 6, exponential and logarithmic functions, let's talk some more about logarithms. So Section 6.5 is properties of logarithms. So our objectives, first, to work with the properties of logarithms. Then we're going to practice and write a logarithmic expression as a sum or difference of logs. So that's usually called expanding a logarithmic expression. Then we're also going to go the other direction, which is to write a logarithmic expression with multiple logs as a single logarithm. And then the last objective in this section is to evaluate logarithms whose base is neither 10 nor e. Because you probably noticed that on your calculator you only have base 10 and base e, but we have a nifty tool called the change of base formula that allows us to work in other bases if need be. So remember the back and forth that if y equals log base a of x, then it has to be true that base a to the power of y equals x. So you might want to write this over and over again. For instance, if I was doing homework, I would write this at the top of each page of my homework, or at the beginning of each problem in the homework, to just get it really solid in my brain. So let's use this to show what is the log base a of the number 1. Okay, so we're looking for a to some power equals 1, right? So let's think about what the power has to be. And the only number that's going to work, think about your properties of exponents, only a to the 0 will equal 1. So the log in any base of the number 1 has to be 0 because a to the 0 equals 1. So this is an important property of logarithms, that the log in any base of the number 1, the output, is 0. So you can get 0 as an output, but you cannot put 0 in as an input. Okay, so then let's look at this other property. This says a to the question mark equals a. Well, we can write a as a to the 1. So clearly question mark must equal 1. So the log base a of a is 1. So that's another property of logarithms. No matter what the base is, if you take the log of 1, you get 0. If you take the log of the base, so the log in base 5 of 5 is 1. The log in base 7 of 7 is 1, and so on, no matter what the base is. Okay, so we have this theorem that's the properties of logarithms. And this follows, they can all be proved, they follows from the properties of exponents. So here is doing and undoing again, which is function and inverse function. So capital M and A are positive real numbers with A not equal to 1. So remember, we keep making that condition on our bases that A is greater than 0 but not equal to 1. So we want positive numbers but not 1 for a base. But a half could be a base, or 1/3 could be a base. That's perfectly fine. But R is any real number. Okay, so make sure you're clear on what can be what. So the number that's represented by log base A of capital M is the exponent that you raise A to so that you get back M. So remember we talked about that the logarithm and the exponent are inverse functions of each other. So does that make sense that if you do the logarithm of something and then you do a to the power of that, you get back capital M. So think about that. Make sure it makes sense to you. So then it's also true that if I have a raised to a power, and I want the log base A of that, it's going to be R. And let's think about why that would be. Log base A of A equals something. This is A to the R. So A to the question mark equals A to the R. Well, it's pretty clear that question mark has to be R. So the log in base A of A to the R is R. So let's look at some specific examples. If I have 2 to log base 2 of 7, do you see that that's going to be 7? So some people think about those things canceling each other out, which is an okay way to think about it. It's really not completely correct. It's really a doing and undoing and not a canceling, really. But it's okay if you think about it that way. Okay, so then let's look at, what if I do log base 3 of 3 to the 6? That's going to be 6. So make sure you're seeing the pattern of which letters go where and what matches up. Okay, so there's some other useful properties of logarithms. And I'm sure you've been exposed to these before, but it usually helps to review the properties before we need to use them again. So capital M and capital N and A are positive real numbers. A not equal to 1, because that keeps being the base. And R is any real number. So remember that the log of a product equals the sum of the logs. And this flows right from properties of exponents. Think about if I have a to the m times a to the n, it equals a to the m plus n. So that's why I have a plus here and a times here. So really remembering logarithms are exponents. So we're saying add these two exponents together. Oh, okay. It really comes from that they're exponents. Okay, so then the log of a quotient equals the difference of the logs. So the log of a quotient of m over n equals the log base a of m minus the log base a of n. So if I have log base 3 of 7x, that equals the log base 3 of 7 plus the log base 3 of x. So usually this is called expanding logarithms. So then we also have that the log of a power, so if I have a log of something to a power, it equals the product of the power, the r, times the log base a of m. Okay, so if I have the log base 4 of 6 to the x, that equals x times the log base 4 of 6. So how I see it, this power comes down into the front as a multiplier. So remember that this is only going to be true, though, if the entire argument is raised to the power. So if I have it like this with parentheses, this does equal 3 log base 7 of a times b. But if I have log base 7 of ab cubed, well, now this is not going to, I can't bring the exponent down in the front because it's not being applied to the entire argument. So here m is called the argument. And the exponent has to go on the whole argument for this property to apply. So this second one would be log base 7 of a plus log base 7 of b cubed. And now the 3 could come down in the front of just the log base 7 of the b. Okay, and then we also know that a to the r equals e to the power of r times the ln of a. So if we use this property the other direction and say, well, r times the ln of a equals the ln of a to the r, so that's using this property from right to left. So make sure you see that it can be used either direction. Well, if I do a to the r, let's see, so that's the same thing as e to the ln of a to the r. oh, well, ln and e to the power of are inverse functions of each other. So make sure you see how this works. This is inverse functions at work, and the other is properties of logarithms. Okay, so then let's work on writing logarithmic expression as a sum or difference of logarithms. So use the properties of logs to rewrite logarithmic expressions. And if we rewrite a single logarithm as a sum or difference of logarithms, we say we are expanding the logarithm. And you might want to know, why do we need to do these two different things we do with logarithms? Well, the expanding the logarithm part turns out it's really, really useful in calculus. It makes your life so much simpler if you will remember this property of logarithms. That's the main place that you use this property. So the opposite task is rewriting an expression with more than one log as an expression with a single logarithm, and both are useful. So expanding is useful for doing calculus. It will be very handy for that, make your life so much easier. And compressing is useful when solving exponential equations. Oh, sorry, logarithmic equations. Okay, so we're just going to practice doing that for a little bit here. So we have the ln of the product of two things. So that's the ln of the x squared times the ln of the square root of 1 minus x, plus, by the properties of logarithms. Now the 2 exponent can come down in the front by properties of exponents, plus the ln of, we can write this as 1 minus x to the power of 1/2. So then we can bring the exponent down in the front as a multiplier. And now we have expanded this logarithmic expression. Okay, and we'll do number 50 in class together. So here's the opposite direction, writing the expression as a single logarithm. Well, notice that those properties of logarithms said log base b of a of m plus log base a of n equaled log base a of mn. Well, there's nothing multiplying here. You can't have any multipliers here. So in fact, the first thing you need to do here is bring this 2 back up as an exponent. So it looks like I have log base 3 of u squared minus log base 3 of v. So now I see I have a quotient property happening. So I'll have u squared over v. So I'm turning the difference of two logs into the log of a quotient. So those properties of logs work both directions. Okay, and we'll do number 62 together in class. And then here's a couple of other useful properties of logarithms. So these probably just seem very logical that, so these are more properties of logarithms. If capital M equals capital N, then what this says is that you can take the log of both sides of an equation. So this theorem gives us permission to do that. So this can be proved. As I've said several times now, we're not doing a lot of proofs, but it's also true that if you can write that two logarithms are equal to each other with the bases the same, then the arguments have to be the same. So these can be used for solving the simpler exponential and logarithmic equations. Okay, so we also want to be able to evaluate logarithms. So evaluate logs whose base is neither 10 nor e. So you probably noticed that the only buttons your calculator has is for e and 10. So we're going to take some time to talk about those two in just a moment.